In this session, we're going to review solving 2x2 systems of equations. This is two equations with two unknowns. Recall that there are three techniques for solving a 2x2 system. We can solve by graphing, and that starts with graphing both lines and writing down the point where they intersect. We can solve by addition or elimination, where you add equations together, maybe after multiplying by a constant, to eliminate a variable. And we can solve by substitution, where you solve for one variable and then substitute that variable in the other equation. Since this is just review, that's all the background you get. We're going to jump in. Solve the system of equations by graphing. 2x minus y equals 5. 2x plus 3y equals 9. On tests, you know what a lot of people do? Elimination or substitution, and they don't graph. If I say solve by graphing, you're supposed to graph and then write down the solution. In a case like this, it makes sense to me to solve for y. Put things into y equals mx plus b form and then graph using the slope and the y-intercept. Sometimes it's easier to graph using intercepts, but these equations lend themselves to the former. So, looking at 2x minus y equals 5, this could be rewritten after solving for y as y equals 2x minus 5, which has a y-intercept of 0, 5, and a slope of 2. And so, using that slope, I find other points to plot, paying special attention to the fact that since I'm looking for a point of intersection, my graph should be pretty darn accurate. I'm going to label this line y equals 2x minus 5, because once I have both of them on the plane, it might be useful to be able to distinguish one from the other. And that looks like it says plus. Now it looks like it says minus. And then the other line, which I'll do, I suppose, in a different color. If I solve 2x plus 3y equals 9 for y, I get y equals negative 2/3 x plus 3, which you should verify on your own. And this has a y-intercept of 0, 3, and a slope of negative 2/3. And so I'm going down 2 and to the right 3 to generate more points. And then I'm going to connect those with a line. And then I'll label that line y equals negative 2/3 x plus 3. I could have used the original equations as given, but it doesn't really matter. What does matter is that I see a point of intersection. And that point is the point 3, 1. But since we're solving a system, I should write this down as an ordered pair, and actually an ordered pair equation. So I'm saying xy, the ordered pair, is equal to the ordered pair 3, 1. That's how a solution to a system of two equations and two unknowns should be given. Next, we're given instructions: solve the system by addition or elimination. Different books call them different things. I use both because you're adding to eliminate a variable. Our system is x over 2 plus y over 4 is equal to negative 2, and 3x over 2 plus y over 5 is equal to negative 6. Your first thought, ew, fractions. So clear them. I'll multiply the first equation by 4 and the second equation by 10, their respective least common denominators. And now I have the system 2x plus y is equal to negative 8, 15x plus 2y is equal to negative 60. And while we have cleared the fractions, if I add or subtract equations right now, I will not eliminate a variable. It seems to me that it would be easiest to eliminate the y's, and to do so I would need to multiply the first equation by negative 2. So if I multiply that first equation by negative 2, I will be adding 15x plus 2y equals negative 60, and then the result of multiplying, negative 4x minus 2y equals 16. I'll be adding those two equations together. When I do, the y terms subtract out, and I have 11x is equal to negative 44. Dividing by 11 gives me that x is equal to negative 4. And now I have x. I can put that into any equation here that has x and y in it. I'm going to go for the equation 2x plus y equals negative 8 because that'll give me y most directly. Substituting negative 4 for x will give me negative 8 plus y is equal to negative 8, which means that y is equal to 0. Tidying this up, we have that x, y is equal to negative 4, 0. Of course, if we wanted to check this solution, make sure that we have a correct answer, what we would do is put negative 4 in place of x in the original equations, both of them. And then we would put 0 in place of y into both original equations. And the reason I say original equations is when we multiplied the first one by 4, we could have made a mistake. And then what I would want to make sure is that after simplifying, I end up with a true statement for both equations. Remember, this is where x and y match for both equations, and so the point should check for both equations. Next, we're going to solve a system by substitution, the system being 3x plus 3y equals negative 1, 4x plus y equals 8/3. To solve by substitution, what I want to do is pick a variable and isolate it, and then substitute. Because in the second equation, I have 4x plus y equals 8/3, I'm going to pick that equation to solve for y. That gives me y equals negative 4x plus 8/3. The order of the terms, negative 4x, 8/3, is irrelevant. I just did that because I'm used to y equals mx plus b form. Now, though, I'm going to take that expression for y and substitute in the other equation. You always have to mix and match here. Never put it back into the same equation. When I do that, I have 3x plus 3 times the quantity of negative 4x plus 8/3 is equal to negative 1. Distributing the 3 gives me 3x minus 12x plus 8 equals negative 1. Collecting my like terms on the left-hand side gives me negative 9x. Subtracting 8 from both sides gives me equals negative 9. And solving that equation gives me that x is equal to 1. Now we have an expression for y in terms of x. And so I can directly substitute. Y is equal to negative 4 times 1 plus 8/3. That's called back substitution. And then getting common denominators, I have that y is equal to negative 4/3. We're again going to wrap this up. X, y is equal to 1, negative 4/3. Next, we're going to look at a couple of special cases. We have a system negative 3x plus 5y equals 2, and then 9x minus 15y equals negative 6. Because nothing looks like it's easy to solve for, that is, it doesn't look like there's a variable that wants to be isolated, I'm going to go ahead and multiply the first equation by 3 so that when I add, I can eliminate a variable. That turns the first equation into negative 9x plus 15y equals 6. That second equation was 9x minus 15y equals negative 6. It was undoctored, we didn't have to change it. Ultimately, though, this gives me that 0 is equal to 0. That's a true statement. A true statement is also known as an identity. And this is what is known as a dependent system, which you may know means infinitely many solutions. What this really means is that we have the same line twice. If you were to graph this, you'd be graphing one line on top of the other one. And in that case, what we want to say is the solution is the set of ordered pairs that are on the line. The way we write that down is we say it's the set, so curly brace, of ordered pairs x comma y, such that, and the way we say that x, y is on the line is we just write down one of the equations. negative 3x plus 5y is equal to 2, and that's it. So when you have a dependent 2 by 2 system, all you need to do is you need to write down the equation of the line and wrap the set notation around it and say it's the set of ordered pairs such that they're on the line. Suppose, though, we had started with negative 3x plus 5y equals 2, 9x minus 15y equals 6. Then taking the same step of multiplying the first equation by 3 would yield me the same doctored first equation, negative 9x plus 15y equals 6, and then 9x minus 15y equals 6. But when I add those two together, the left-hand side, the variables eliminate each other. The right-hand side, I have 12. 0 is equal to 12. No, it's not. This is a false statement, also known as a contradiction, which makes it what we call an inconsistent system, which means there is no solution. You can choose to write the words no solution, or you can give me the set equivalent, which is, that zero looking thing with a slash through it, which means the empty set. The solution set is empty. And if, generally speaking, the variable drops out and you have a false statement, then you will have no solution because it's a contradiction. If the variable drops out and you have a true statement, then what you have is a dependent system, and then you'll phrase your answer in the appropriate terms.